Now what we want to look at is we want to look at approximating areas. So we're switching now to do something slightly different. Now that we have the notation down, we're going to look at approximating areas under a curve, between a curve and the x-axis. So we're going to start with assumptions that actually don't have to be in place. And we're eventually going to relax these assumptions and show what the minimum assumption is for it to work. But we're going to start with a more rigorous assumption, which is that the function is continuous. And that means the function exists, the two-sided limit exists, the function equals the two-sided limit. Formal definition. Informal definition, you can draw it without picking up your pencil. That eliminates the 4 discontinuities: jumps, displaced points, holes, and vertical asymptotes. So we have none of the 4. As we're going to discover, it actually can deal with 3 of those. It can deal with jumps, holes, and displaced points. The vertical asymptote, unfortunately, it cannot deal with. So we'll discover that that one will always be a requirement, that it not have those. We want to approximate the area that is below the function, above the x-axis, and between the vertical line x equal a and the vertical line x equal b. So again, right here, you have a vertical line, and that's x equal a. Remember, the formula for a vertical line is x equal a constant. And then right here, you have the vertical line x equal b. And we're looking for the amount of area, the amount of paint it would take to shade in this blue region right here. Now, what we're going to do is we're going to subdivide it into intervals of some given length. Now, technically, they don't have to be the same length, but it does make the calculation easier if they are. So what do I mean by we're going to subdivide it into lengths? I mean that we're going to take the x-axis and we're going to divide it into little subintervals. And we're going to let this be A be the first one. And we're going to let the next one be x sub 1, x sub 2, x sub 3, x sub 4. And on my picture, the last one is x sub 5, which is B, because I'm dividing it into 5 partitions. Now, partition means a part of something. And in theory, these do not need to be the same length. They could all be different lengths. There will be a restriction that the widest one eventually goes towards 0, because we're going to take more and more partitions. The more parts you divide it into, the better your approximation is going to be. And then we're going to draw vertical lines that, oh boy, that was a bad vertical line. Vertical lines that hopefully stay more or less vertical from that point back. Okay, I need a straight edge. My vertical lines aren't remotely vertical today. Okay, there, that's better. They go up to the curve. God, now the other 2 look so awful. I got to redo them. Okay. We all know I cannot draw. That is for sure. My parents despaired of me even as early as kindergarten. They were like, oh my gosh, this kid cannot draw. She can't draw and she can't sing. And what does she love to do? Draw and sing. Okay, so we're looking at this right here. We want to approximate with rectangles. Now, there are a couple of different ways of dividing up the rectangles. We can use the left side or the right side for the height of the triangle, or we can use the midpoint, or we could just take some arbitrary point inside that interval and say, this is the height. So it doesn't really matter where we do it. I could say, I'm taking the height right there. So I'm going to come across and make that high. And on this one, I'm going to use the left endpoint. So I'm using all different values. And on this one, I'm going to use the right endpoint. And on this one, I'm going to use the middle. And on this one, I'll use the middle again. So it's a little over on the left and a little under on the right. Now, in theory, okay? In theory, it doesn't matter if you choose a different x sub k in each of the partitions. That is allowed. You can choose a different point to evaluate the height of the rectangle at any point. In practice, not theory, but in practice, we tend to always choose the same place to make it easier to compute. So we always choose the left side, or we always choose the right side, or we always choose the midpoint. Those are the three most common places to choose: left side, right side, midpoint, because they're easy to compute. Can you tell that this is going to approximate the area under the curve? Now, there are some places like here where I've got white space showing where I'm overestimating what the area is. But then there are some here where there's blue that's not under the rectangle. That's an underestimation. So the hope is that the overestimations and underestimations will kind of even out and you'll get close to the area under the curve. Now, by taking more and more rectangles, you can get closer and closer. So this is what we call a partition, where we divide the x-axis up into x sub 0, x1, x2, x3, x4, x5, x sub k, all the way up to x sub n, which is the last one, equal to b. And then this makes it divided into intervals: x sub 0 to x sub 1, x sub 1 to x2, x2 to x3, x3 to x4, xk minus 1 to xk, xk to xk plus 1, all the way up to x sub n minus 1 and x sub n. So it makes these closed intervals that we use to be the vertical lines that become the sides of our rectangles. All right. And then we choose a point within each of these closed intervals to be the height. We take the function value at one of those points and we say, you're the height of this rectangle. This is called a partition. Now, a regular partition is one where all of these sub intervals, x sub 0 to x1, x1 to x2, x2 to x3, x3 to x4, and so on, are all the same length. So regular means you divided it up so that they're all the same width. All right. That's not technically required, but it does make your job easier. So how do we know when we divide it up into that what we're going to get? Well, we can take b minus a and divide it by n, and this would make them all the same width. Same width intervals on the partition. And we call that value, when you take b minus a and divide by n, we call that the change in x, or delta x. All right, so it's called the change in x, or delta x. This formula that you see right here is important. You need to memorize that. It's pretty straightforward. I mean, how do you average stuff? You take b minus a and you divide by n. Take the n, take the beginning, divide by n. All right. So for example, let's say you were looking at the interval from 1 to 10 and you wanted 3 partitions. How wide should each one be? Delta x would be, well, this is a, this is b. So it'd be 10 minus 1 divided by 3, which is 3. So your partitions should go from 1 to 4, 4 to 7, and then 7 to 10, each of them being 3 long. Now let's define for us what's called a Riemann sum. Now, if we want the kth point coming across, then we start at A and we add the change in the width of each interval, delta x, times k, to get us over to x sub k. So remember that you're dividing the subintervals down here into x sub 0, x sub 1, x sub 2, and so on. So x sub k means start at A and add delta x k times, and that will get you to the kth one. All right, so let me do an example of that. So here's our number line, x sub 0, x1, x2, x3, x4, x5, and let's do x6. So how do I get to x5? x5 is equal to A, which is x naught, plus delta x times k. So this would be A plus delta x times 5. So I add delta x one time here. I add delta x another time here. Delta x another time there, that's 3, 4, 5. And that brings me to x sub 5. All right, so whatever A is, if I add delta x 5 times, I'll get to x sub 5. So that's a formula that gets us out there to x sub k. Then we take the height at some particular point in the interval. We haven't specified what that point is, so we're going to take the height at x sub k star. So just some special point inside the kth subinterval. So that's a star or an asterisk, really. So the k is a subscript and the star is in the power position, if you're wondering how to write it. So the k is a subscript and this asterisk is in the power position. And it means take some special point, x sub k star, in the kth interval, and that's the height. Now let's take a look at these. This is what's known as a left Riemann sum. And this is what's known as a right Riemann sum. Who can tell me by looking at the pictures what the difference between the left Riemann sum and the right Riemann sum are? Riemann is named for Bernhard Riemann, who was the mathematician, German mathematician, who came up with this way of doing things. Which, by the way, we should probably mention, most of what we study in calculus is the results and the work and the theorems of, let's face it, dead white guys. All right. So why aren't there any women? Why aren't there any African-American Black mathematicians? Why aren't there any Latinx mathematicians? Because in the days when this was being done, which is largely the 1700s and 1800s, the only people who published were the people who were in positions of power. It doesn't mean that there weren't women doing work or that there weren't Latinx people doing work or there weren't Black people doing work. It means that they weren't getting published. In those days, it wasn't who came up with the theorem that got the credit, it was who published it. So many people of color and minoritized groups had their work appropriated, let's put it nicely, by others who were members of the Royal Society. And because they were members of the Royal Society, that mostly meant that they were, first off, lords. All right, so they weren't commoners. They were rich and they were wealthy and they were by and large white landowners. All right, so that's why we don't see women or people of color in calculus studies. It doesn't mean they weren't doing the work. It means their work got appropriated and published under the name of a white man, because otherwise they couldn't get it published. In those days, they didn't have the rights that they have today, and so they simply could not get published. Pretty much if you weren't from Sweden, England, Germany, France, or Italy, you didn't get published. Those were pretty much the only countries that were doing publication in the area of calculus in the Western world. Okay, So a little bit of history there. Looking at this right here, what's the difference between the left Riemann sum and the right Riemann sum?
One will like exceed the area and one will be short of.
Yes, so Juan has pointed out something very important. On an increasing function, the left Riemann sum is underestimating the area, and the right Riemann sum is overestimating the area. So this is a very, very important fact. When you have an increasing function, a left Riemann sum underestimates and a right Riemann sum overestimates. If you have a decreasing function, it's the reverse. The left Riemann sum overestimates and the right Riemann sum underestimates. So we see a difference in their estimation pattern. One's over, one's under. What about the height at which the function is taking the height of the rectangle? What's different between the left Riemann sum and the right Riemann sum? Let me draw out here your intervals. We have x0 to x1, x1 to x2. So this is x1, x2, x3, and x4. It's the same on both. All right. X2 to x3, x3 to x4, and that's it. Okay, almost got carried away there. And over here we have the same partitions, x0 to x1, x1 to x2, x2 to x3, and x3 to x4. On the left Riemann sum, which ones are used for the height of the rectangle? Which endpoints? In the first partition, which is x0 to x1, which one gets used for the height?
X0.
X0. In the second partition, x1 to x2, what gets used for the height?
X1.
X1. Excellent. And then, oops, I erased back. Every time I do that, it wonks off somewhere else. Okay. What about in the third partition? Do we see a pattern developing? In x2 to x3, what gets used for the height of that rectangle? The left endpoint of the interval, x2. And for the last one, between x3 and x4, what gets used for the height of that? x3. So our left endpoints are x sub 0, x1, x2, and x3, but not x4. x4 is never a left endpoint, it's only a right endpoint. What about on the right Riemann sum? Our first partition is again from x0 to x1. What gets used for the height of the first rectangle? Look at the top where it intersects the graph. Where does it get used for the height?
X1.
X1, the right endpoint. In the second partition, it's x2. In the third, it's x3. And in the last one, it's x4. So the right endpoints are the right endpoints of the subinterval x1, x2, x3, x4. That's why it's called a right Riemann sum. You're using the right endpoint of the interval. What if they took the midpoint? What do you suppose they would call it then? Midpoint Riemann Sum. That's exactly what they'd call it. All right. And they would be using the midpoint. And we'll see one of those in a minute. So the difference between the left and the right Riemann sum, the left on an increasing function underestimates the area, and the right Riemann sum overestimates the area. The left Riemann sum uses the left endpoint of each partition to calculate the height of the rectangle. And the right Riemann sum uses the right endpoint of each partition to calculate the height of the rectangle. If we repeat that process and we add them all together, we should get a good approximation for the area under the curve. These are called Riemann sums. There's a left, a right, and a midpoint. And here's the theorem. Suppose that we have a function f and it's defined on a closed interval, because again, we want to make sure that it's defined, all right, so that we can find the value of the function at the left or the right endpoint so that we can get the height of the rectangle. It is divided into n subintervals of equal length. So this is a regular partition. Delta x is b minus a divided by n. If x sub k star is any point in the kth subinterval or the kth partition, x sub k minus 1 up to x sub k, for k going from 1 to n, because we have n partitions, n rectangles, then the Riemann sum is given by this expression right here. And notice that this is a summation. So we have f of x sub 1 star, height of the rectangle, times delta x, width of the rectangle. So looking at our picture right here, oops, wrong color. I need black. This is f of x sub 0, and this distance is delta x. So the area, if I can write this sideways, is delta x f of x sub 0, all right? The area of a rectangle is the length times the width. So delta x times f of x sub 0. The area of the second box is also delta x, since they're the same, times f of x sub 1. And then we have delta x times f of x sub 2. And then delta x times f of x sub 3. And if I want the area of all of those, I just add them together. So coming down here, I have f of x sub 1 star. This is allowing it to be left or right or midpoint or totally random, times delta x, plus f of x sub 2 star delta x, all the way up to the last partition, the last subinterval, the nth one, f of x sub n star, height of the box, width of the box, which gives us the Riemann sum from k equal 1 to n of f of x sub k star delta x, which gives us a formula to find it. So a left Riemann sum is done this way. And there's a formula for writing a Riemann sum, which is this formula right here. This will give you all of the left endpoints of your subinterval. So the first subinterval, if you're doing left endpoints, is x sub 0. So you don't want to add delta x. So the first one, you're going to have k, which is 1, minus 1, which is 0. So you just get a. So the first one is a equal to x sub 0. So you get a list a, which is x sub 0, then x1, then x2, then x3. How far did we go? 1, 2, 3, 4. So it just goes up to x sub 3, and then it stops because we want 4 rectangles. So 4 minus 1 is 3. 3 delta x adds delta x, delta x, delta x, and brings us to the fourth one. All right, so that's a formula for it. We can do the same thing for the right Riemann sum. On the right Riemann sum, you don't start at a, you want to start at the next one over. So you want k delta x, because you need to add delta x to the left point where you start. So you're going to start with x sub 1. So this would generate x1, x2, x3, and x4. Those would be your 4 places where you evaluate the height of the rectangle. Okay. Now, most of the time when we do these, we're going to do them by hand. So it will be pretty easy just to look at the graph and figure out what they are. You won't have to worry so much about the summation. We'll only work with the summation a couple of times. But again, we want to introduce the summation notation to you because it is critically important in Calculus 2. So if you have to take Calculus 2, be sure you spend some time on that summation notation and take hold of those notes and keep them. You're going to want them when you get into Calculus 2. Now we have a midpoint Riemann sum. Your book doesn't cover this yet. It actually covers it in Calculus 2, which I always thought was kind of stupid. It should be here. So we're covering it here. All right, so the midpoint says basically you want to take k delta x's and then back up half of 1. All right, so another way of writing this formula is x sub k star is equal to a plus k delta x, which would put it at the right endpoint, minus half a delta x, not k. Back up half of 1. All right, so go to the right endpoint. That's what the first thing does. Then back up half the width of the partition. Back up halfway. And that will give you the midpoints, which are here, 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 and here, giving you the middle of each interval as the point where you calculate the height of the rectangle. Now, looking at this particular one right here, can anyone tell me the advantage of a midpoint Riemann sum over a left Riemann sum or a right Riemann sum? We have the same increasing function as we had before. How is this one better? Because it is better. How is this one better than the left or the right Riemann sum?
So isn't it dividing the section or the interval into like more pieces?
No, it's still 4. We still have 4 boxes.
As you're overestimating and underestimating at the same time.
Okay, Caleb says you're both over and underestimating on each partition, and he's correct. So when you're looking at this for an increasing function, look at the top of the box. Do you see how on the second partition, we have a little bit of blue area that sticks above the function? That's an overestimation. But on the right side of the midpoint, we have a little bit of white area, which is under the function. That's an underestimation. So the midpoint is averaging the error on each individual rectangle. Does that make sense? The midpoint Riemann sum averages the error on each individual rectangle for a strictly increasing or strictly decreasing function. In general, the midpoint Riemann sum is one of the best ones you can use, one of the most accurate ones. Left Riemann sum and right Riemann sum are less accurate. Midpoint Riemann sum is very accurate. And I'm going to show you some different ways of doing it. There are 2 others that you will learn in Calculus 2 called the Trapezoidal Rule and the Simpson's Rule. And I'll show you different ways of doing those. Okay. So basically for an increasing function, the left Riemann sum underestimates, the right Riemann sum overestimates, and the midpoint Riemann sum is closest. It's neither an under or overestimation consistently. It depends on the curvature of the function. So it kind of averages out the area and tends to be more accurate. Now I've gathered for you some examples. Oh, I did some decreasing ones as well, so you can see what it looks like on decreasing. The book didn't have any decreasing pictures, so I created some for you. This is a strictly decreasing function. I should have made it a color other than purple, but at any rate, it's purple coming down here, the dark line. Michael, hopefully you can see this. It's darker, all right? So it's coming down like this. And this first one is a left Riemann sum. So we have a left Riemann sum for the first one. The second one is a right Riemann sum. Notice that for a decreasing function, the left Riemann sum overestimates instead of underestimates, and the right Riemann sum underestimates. And what happens again on the midpoint? It averages out the error. Has a little under, has a little over, both. So it kind of averages the error out. So the midpoint Riemann sum is a better approximation compared to the left or the right on a strictly increasing or decreasing function. In general, it is the most accurate. Okay, now I do have some online calculators for you that you might want to play with. I have a bunch of different ones listed here. The left Riemann sum, the simplest one to use here is the second one. The first one we'll use later on for area between curves. It's more complicated. So I recommend that you use the second one. Then I only have one for a right Riemann sum. This is on Desmos. And then I have one for a midpoint Riemann sum on Desmos as well. And then I've got some that do all three. All right, one on Desmos and two on Geogebra. Now, when it does all three, it gets a lot more complicated. All right, so I want to talk about some of these. So let's take a look at which ones I've got open. I think I have open the three down here at the bottom. So here's one of the Geogebra ones. This is the one that ends in DK4Y. That's the second one. All right, the Geogebra listed first. All right. Now, what's nice about this one, when you're looking at this one, I have a function in here. The function is x cubed minus 2x squared plus x plus 1. Right? And I will copy this off and put it in the chat window so that you can come and see it. Okay, so take a look at that. Hopefully that will give you the one with the function that I've got. Now, what do I like about this one? Why is this one of my favorite ones? For one thing, it's a nice clean picture. It's not too crowded with lots of grid lines and stuff, which Desmos has lots of grid lines. You can take them off, but this is nice and clean. It does show the partitions coming up to the height right here. And on the left, you have the choice to show different things. The left is A, the right is B. So left equals A, right equals B, and N is the number of boxes you want. So I'm going from 0 to 2 with 9 boxes. Show divisions gives me the 9 divisions for my 9 partitions. And then I have a choice of a left, right, midpoint, trapezoidal, or Simpson's rule. So let me show you left Riemann sum. All right. So I'm going to blow it up a little bit so you can see it a little better. There we go. So while you're looking at this, this is a left Riemann sum. So I clicked on left Riemann sum, and it's giving me the actual sum value. Yes, this is how you can get answers to your web work homework problems without actually doing it. But you need to understand what you're doing so you can do it on an exam. So it's taking the height at the left endpoint and multiplying by delta x. So we have 2 minus 0, b minus a, divided by n, which is 2/9. So each of these boxes is 2/9 wide, and there are 9 of them. That's the left Riemann sum. Does everybody see it's using the left endpoint for the height of the box? Now let's change left Riemann sum to right Riemann sum. And yes, you can show them both at the same time, but I just want one at a time. So now it's giving me the sum of the right Riemann sum, where I'm using the right endpoint of each partition to draw the height of the box. And you can tell that when it's increasing, it's an overestimation. When it's decreasing, it's an underestimation. So let's click back on the values and see what we've got. 2.9 for this one, 2.46 for that one, 2.5. So they're off. Now let's look at the midpoint, which we know is more accurate, and the values between those two. So I had 2.49 and 2.9? 2.8, 2.9, I can't remember. 2.65844 is between the two. You can tell that it is sort of averaging out the error on each individual partition, part over, part under on each one. And that's 2.6844. Now let's take a look at the trapezoidal rule, just so you have an idea of what it is. Now, what does the trapezoidal rule do? Look at the first box. Do you see how it's made a straight line connecting the two endpoints? That's what the trapezoidal rule does. And I'm going to decrease the number of boxes so that you can see it a little better. It makes straight lines between the endpoints, which turns each individual rectangle into a trapezoid. It's not a rectangle because these two sides are no longer parallel, but it's a trapezoid because these two sides are parallel. So the vertical sides of the box are still parallel. These two sides aren't. So you find the area of a trapezoid instead of the area of a rectangle. Then you add them up, you can tell that this is doing a better job of finding the error, right? It's doing a better job of finding the area and minimizing the error. What about Simpson's rule? 2.75. Simpson's rule, it's not showing the picture. Rats, I hoped it would. It's not showing our picture. Let me go up to, is it going to show? No, it's not. For Simpson's rule, you have to have an even number. And what it does is it takes pairs of boxes and does a parabola on the top. So it takes a big rectangle made up of two partitions with a parabola connecting the 3 points at the top. And this gives a curved edge instead of a straight edge, which can be more accurate. Now, we said that the midpoint was 2.66204. Trapezoid was 2.67. Those are all three relatively close. The left Riemann sum and the right Riemann sum are further off. The actual value is in the integral down here. So what we're leading to next in our section 5.2 is this, which is the definite integral. The definite integral is different from the indefinite integral, completely different. The indefinite integral is a family of functions whose derivative gives you back the integrand. So you always get a function plus c. And definite integral has numbers on the summation or the integral symbol, which represents the summation symbol. So it's a Riemann sum, and you've taken the limit and you're going from 0 to 2. This gives you not a family of functions, but an actual number, and the number represents the area under the curve. All right. So that's one of my favorite ones. I like this one because it connects it to the definite integral. There's another one right here, which only does the left Riemann sum, which it calls, left Riemann sum. It calls the lower sum. And then the upper sum. All right. And then the midpoint sum. This is not my favorite one. I don't use this one as often. It's the other Geogebra one. There is one on Desmos that I do use, and this is this one here with SULII at the end. So let me share this screen with you. This is the Desmos one I use. All right, so it's in the chat window. So when we're looking at this one right here, you have your function, which you put in at f of x. N is how many subdivisions you want. This is the same function, so let's go down to 9. All right, so now it looks like the previous. And then you have a choice within the same program. You can choose a left Riemann sum, a midpoint Riemann sum, or a right Riemann sum. So m equals 0 is the left Riemann sum. And then if you move it, it's a drag the bar, which it's not wanting to drag. I'll change it this way. If you make it 0.5, it becomes a midpoint Riemann sum. And then if you make it 1, it becomes a right Riemann sum. Okay. Now, it does have one other aspect, which is nice, which is down here, it gives you the value of delta x. So delta x is 2/9, which is 9 divided by 2, or 2 divided by 9. Sorry, got that upside down. Okay. And then it labels A and B. All right. So A is the left endpoint, B is the right endpoint, ignore C, leave C where it is. And all you'll change is the function, the number of boxes, which Riemann sum you want, the value of A and the value of B. Those are the only things that you will change. Okay. So I recommend really the first one, which is the GeoGebra one. I think this one is easier to use for students because you just have to click a box to get the one you want. Although in some ways the pictures on Desmos are slightly better than the pictures on GeoGebra, but I think the functionality of this one is better. Plus, I like the connection with the definite integral. Okay. Now, there is a section in the notes that covers doing Riemann sums on a graphing calculator. So everybody take out your graphing calculator and let's talk about doing Riemann sums on graphing calculators. First off, we need to find out if you have the one that has the sigma symbol on it. If you do, then you're much, much better off. So turn your calculator on and click on the math button. So when you're on the calculator and you click on the math button, I'm going to change my video to the closer one. Okay. So it should say math. And now I want you to scroll down to probably number 0. So scroll down by pushing the down arrow and see if you get a summation with a sigma symbol at the bottom. How many of you do not have the sigma symbol? Put a don't in the chat window if you don't have that.
How do you get to that page for the math?
You click on math right here.
Gotcha.
Click math right there and then use your cursor key. Can't do this one-handed. Use your cursor key right here to scroll down till you get to that. Okay, so if you have the sigma notation, then you're lucky because you can enter whatever you want. So you want to set up the variable to be the index of summation. So click x equal, and let's go from 1 to, and then click up, maybe 25 of x. All right, so enter something like this if you have that. 1 through 25 of x, and then hit enter. And you should get 325. Now, some of you do not have that. So what you need to do instead is go to the main screen. So exit out of that math screen by doing second mode, which is quit. And then from the main screen, hit the second button, then hit the stat button. So second and then stat to get to list, and it's going to show list up there. All right. And it's going to say names, ops, and math. Move the cursor 2 to the right to get to math. Second stat, cursor 2 to the right to get to math. And those of you who have the sigma symbol, you can practice this too. Then hit number 5 or scroll down to highlight 5 and then hit enter. And it's going to put out on your screen sum. So this is the sigma symbol. And then you need to do a sequence. So you're going to come back to the list command by hitting second stat again. So second and then stat. So you're going to hit the second button and then you're going to hit the stat button, which is right there again. But instead of going to math, you want to go to ops. So just 1 to the right. Again, scroll down to number 5 and hit enter, or just type in 5 to get sequence. A sequence is an ordered list of numbers. Now, mine has this page. Not everybody's does. Some of yours now says sum, parentheses, sequence, parentheses. If it does, then you're going to follow the same steps I'm following, but it's going to look slightly different. So our expression behind the summand is just X. So just enter X. If you don't have a screen that looks like mine, yours is all on the main screen, sum, parentheses, sequence, parentheses, X, put a comma. All right. And then if you have one that looks like mine, the next thing you have to put in is the variable, which is X. So you should have X, comma, X, comma. And then we started at 1, and I think we went to 25, didn't we? So you put in 1, comma, 25. And I'm going to put in 1 down to 25. All right. So you have X, comma, 1, comma, 25, comma, 1. 1 tells it to iterate by 1. So 1, then 2, then 3, then 4. So the last one should be a 1. And then close your 2 parentheses if you have parentheses. Mine just says paste. So I come down here and I click enter on paste. And it's going to give me what you should have. Right? It'll say sum, parentheses, sequence, parentheses, X, comma, 1, comma, 25, comma, 1, parentheses, parentheses. And now hit enter. And we get 325. Okay. Which is how we do a Riemann sum on the calculator.
Now let's switch gears and talk about what a Riemann sum is, a left Riemann sum and a right Riemann sum.
Doing a left Riemann sum for the function x squared plus 3x by hand over the interval from 3 to 5 using n equal 4 rectangles. So what we're going to do is we want to know what x squared plus 3x looks like. We're just going to sketch the graph. So we have x squared plus 3x. And I know from college algebra that this factors to x times x plus 3. So it crosses at the origin and it crosses at -3. And so it must have the vertex halfway in between, which would be at -3/2. And so I can plug that into the function and square it and multiply it by 3/2, -3/2. And that gives me 9/4 minus 9/2, which is equal to 9/4 minus 18/4, so -9/4. So a little past -2. So right down here. And this is a parabola, right? Not the greatest picture, but more or less looks something like that. And we want to go from 3 to 5 using n equal 4 rectangles. So 1, 2, 3, 4, 5. So I need this to come up to 5. So I'm going from 3 here to 5 here, and I want 4 rectangles. So I can do delta x is equal to b minus a divided by n, which is 5 minus 3 divided by 4, which is 2 divided by 4, which is 1/2. And I'm doing a left Riemann sum, so I'm going to use the left endpoints. So my endpoints are going to go from 3 to 3.5, then from 3.5 to 4, and then from 4 to 4.5, and then from 4.5 to 5. And that gives me 4 subintervals or partitions. Each one is half a unit long. And for a left Riemann sum, I'm going to use the left endpoint. So I'm going to use 3, 3.5, 4, and 4.5. So my left endpoint Riemann sum is the sum from k equal 1 to 4 of f of x sub k star times delta x. So my delta x is 1/2. So I have 1/2 times each of the function values. So then I want 1/2 times f of 3 plus 1/2 times f of 3.5 plus 1/2 times f of 4 plus 1/2 of f of 4.5. Those are my 4 left endpoints that I found from my subintervals. Now, the 1/2 is common to all of them. It's the width of the rectangle times the height of the rectangle. So I actually have 4 rectangles in here, which is kind of hard to see. And I'm using the left side to shade it. So it's just going to be this part right here. Just up to the left side where the height of the left side. So it's an underestimation because it's increasing. And because the 1/2 is common, I can factor that out and multiply that by f of 3 plus f of 3.5 plus f of 4 plus f of 4.5. And so now I need to take my function, and the easiest way to do this is to use your graphing calculator. So turn your graphing calculator on, go to mode, make sure you're in function mode, all right? Then go to y equals, and you want to enter your function into y equals. And our function is x squared plus 3x. And we want a standard window, but really we're interested in from 3 to 5. So we can maybe graph it from -3 to 5. So on the window, let's go from -3 up to maybe 7, so we can get a little past. And we're going to let it choose the best scale. So we're going to do a zoom fit, which is zoom. I think it's 0. Yes, zoom 0. It's been a while since I've done this. So now I can see the function coming up. So it'll look something like this. Right? Now what I want to do is I want to calculate the function value at the left endpoints. So I do second trace, which is calculate, or I can set up the table to start at 3 and go by 0.5. It'd probably be better to use the table. So second graph gives me table. Actually, let's go to table set, which is above window. So second table set, and I want to start at 3, and I want my delta table to be 0.5, and then go to table. So this is what my table set looks like. Trying to get it out of that shadow. and then go to table. And you'll see the values coming up. And those are the function values. And so all we need to do now is enter them in. So we have 1/2 times f of 3, which is 18, plus f of 3.5, which is 22.75, plus f of 4, which is 28, plus f of 4.5, which is 33.75. And then we add those values together, and that will give us the value of the left Riemann sum of that function, which comes out to be, if I can get over to my notes over here. I don't actually know. I didn't enter this one in. So 3 to 5. So from 3 to 5, I've got 18 plus 22.75 plus 28 plus 33.75, all divided by 2 or times 1/2. I've got 51.25. As my estimation for the area under the curve between those two values. And that's my left Riemann sum. Now let's repeat the same thing, only this time we're going to use a right Riemann sum. Right? And I think I did give you a link to what it looks like, except I've got A set wrong. It should be going from 3. There we go, from 3 to 5, right? And it estimates what the value is. Right here, it tells you the Riemann sum is 51.25, all right? So when you're looking at the applet, if you scroll down, it has the summation b minus a over n, which is delta x times the function value, which is 51.25. So we know we did that correctly. Now in the next one, we want to compare with a right Riemann sum. This one, we're going to go from 1 to 5 using 4 intervals. So we can copy off our picture again. Let's paste our picture down here. Whoa, that got me a little more than I was expecting. Okay, so we can take all of this off. So now what we want to do is we also want to go from 1 to 5 this time. So we're going from 1 to 5. Oops. There we go. So going from 1 to 5. It's not quite letting me. Okay, I'm just going to leave that one. So this time we go from 1 to 5 and we want the right endpoint. So this is our x sub 0, x1, x2, x3, and x4. And we have delta x equal to b minus a over n, which is 5 minus 1 over 4 boxes, which is 4 over 4. So each box is 1 wide. And we're doing a right Riemann sum. So we're going to come up to the right endpoint height and then come across. So the right endpoint height, and then we come across. Right endpoint height, and then we come across. Right endpoint. So you can tell it's an overestimation. And then we can color this in. So we're definitely overestimating this area here. All right. And again, what we need to do is the Riemann sum. So we do the sum from k equal 1 to 4, because we have 4 boxes. Delta x, f of x sub k star, where x sub k star is the right endpoint. Delta x is a constant, so we can factor delta x out and just take the sum from 1 to 4 of the function values at the right endpoint. So this is going to give us 1 times f of, and let's make a list of our right endpoints. The far left, x sub 0 equals 1, that's A. X1 equals 2, X3 equals 3, X4 equals, wait, 1, 2, 3, X0, X1. Oh, I'm counting wrong. X sub 2 is 3, X sub 3 is 4, and X sub 4 is 5. So we want the right endpoint. So that's 2, 3, 4, and 5. So now we want f of 2 plus f of 3 plus f of 4 plus f of 5, the right endpoints only. Again, come back to your calculator. It's still in the calculator. You just need to change your values, or you can just scroll up and down on the table. So f of 2 is equal to 10. F of 3 is equal to 18. F of 4 is equal to 28. And f of 5 is equal to 40. Right? And if we add those together and find our sum going from 1 to 5 using the right endpoint, we end up with 96. All right. Now, if we look at our left endpoint and we change the lower limit of summation to start at 1, so our interval to start at 1 and go to 5, it estimates 60 for a left Riemann sum on the same interval, which tells you that these are very far apart. The left Riemann sum is estimating 60, which is an underestimation. The right Riemann sum is estimating 96, which is an overestimation. And I do have a link here, which will give you that picture. And I can scroll this out and you can check on this one, and it does tell you that it's 96. Make sure A starts at 1, B goes to 5, and you have 4 boxes, which is the right function. Okay. Now, the next one we want to take a look at is number 8, which is the same thing, but using a midpoint Riemann sum. So we want to use the same interval from 1 to 5. And this time I'm going to redraw the picture because it's taking too long to copy and paste. So I know it goes through here, 2, 3, and here, and it's about down here. So 1, 2, 3, 4, 5. So I'm coming from here to here. But this time, when I look at each of my intervals, I'm going to take the midpoint of the interval for the value where I compute the height of the rectangle. So on this one, I have basically from 1 to 2, from 2 to 3, from 3 to 4, and from 4 to 5. Those are my partitions. Again, delta x is equal to 5 minus 1 divided by 4, which is 4/4 or 1. So they're 1 wide. So this is 1 and this is 5. I need the midpoint of each of those intervals. So my endpoints, or well, let's not call them endpoints. Let's call them height points. my height points are going to be 1.5, 2.5, 3.5, and 4.5. So again, I need the sum from k equal 1 to 4 of delta x times f of x sub k star, where f of x sub k star is now the height points, the midpoints. So again, delta x is a constant, which I can pull out. So on each of these, I'm going to find the middle of the partition and draw the box. So the middle of the partition and draw the box. Middle of the partition and draw the box. So the middle of that partition and draw the box. And then I can shade it. So I have a little under and a little over on each box. Okay, so each box is kind of averaging out the value. Okay, so it looks kind of like that, right? So now when I approximate, my delta x is 1, and I'm going to be adding up f of 1.5 plus f of 2.5 plus f of 3.5 plus f of 4.5. And if you go to your calculator, it should still be in there on the table. So you can do f of 1.5, which is 6.75. F of 2.5, which is 13.75. F of 3.5 is 22.75. And f of 4.5 is 33.75. Now, these I didn't have to plug into the function because they came out exactly. If they don't come out exactly, you may have to actually plug them into the function by hand, right? If they're repeating decimals. So this is going to give me, when I add all of these up, this gives me 77. And notice that this is in between the two estimations I had. The left Riemann sum for that area was 60. The right Riemann sum was 96. 77 is right in the middle. Okay. And we will be learning on Wednesday how to actually compute the true area, in case you're wondering when that's coming. Okay. So the last thing that I wanted to mention was we've been using mostly 4 boxes, maybe 5 boxes up to 9 boxes. But in general, if you look at this picture here, it's got 4 boxes. And then this picture over here, it's got 1, 2, 3, 4, 5, 6, 7, 8 boxes. So this has double the number of boxes. And you can tell that it has less error in it because the amounts that are over and under are less. And these are both midpoint Riemann sums, same function, midpoint. So this is n equal 4 boxes, and this is n equal 8 boxes. And then when you look at the next picture down here, this is n equals 16. Do you see how much more closely this fits with the curve? So that you can tell that the error, which is the amount that's either over or the amount that's under, is minimized. So the more boxes you have, the closer you're going to be to the true area. This is 16 boxes. And then, of course, this one over here, I believe, is n equal 32. I doubled them each time. So when you get to n equal 32, you can tell it's much closer, and it's almost difficult to actually detect the error. You can kind of tell it's there. But again, as the number of rectangles increases, then it makes sense that the area under the curve becomes more precise. So the last idea is this idea of taking the limit as n goes to infinity of the Riemann sum. And as the number of boxes goes to infinity of the Riemann sum, you get the exact area under the curve. So as the number of boxes increases, the width of each box has to decrease when you're looking at these pictures up here, you'll notice that the width of each box is decreasing as I increase the number of boxes, and the number of boxes is going to infinity. And as I do that, I get a better approximation of the true area under the curve. Now, what we're going to talk about next time is how to find and approximate the area under the curve using geometric shapes. And then the day after that, we'll be talking about how to actually compute the area under the curve using the definite integral that we looked at earlier on the applet.